Section 8.1, Graphing f of x equals ax squared. We're moving on beyond linear functions and now talking about quadratic functions. A quadratic function is a non-linear function with a degree of 2, as indicated by the x squared. And it has a standard form equation, y equals ax squared plus bx plus c. When we involve the bx plus c, the graph gets a little bit more complicated, so today we're going to focus just on y equals ax squared. Now we mentioned that this function is nonlinear. The shape of the curve is called a parabola. And this parabola is a U-shaped graph of any quadratic function. So you can see from the diagram here that we have something other than a line, although I do have a vertical line highlighted. I'll mention that in a minute. And I have a point highlighted here, point A. But this is what we're going to be talking about. We're going to learn how to graph these and how to compare the graphs of different parabolas. There are some key characteristics of all parabolas. First of all, we have the vertex. You've probably been able to figure out that the vertex is the point where the parabola completely turns around, indicated here by point A. Based on the coordinate grid that we have, the coordinates of this vertex are 1, -5. The axis of symmetry is a line that cuts directly through the vertex and serves almost as a mirror for the parabola. This is highlighted by the dotted red line. You'll notice that the parabola is symmetric on either side of this axis of symmetry. Since in this case I have a vertical axis of symmetry, it has the equation x equals 1. All vertical lines have equations of this form where x equals a number, and it happens to be the number that is the x-coordinate of the vertex. It's the vertical line that passes through the vertex and serves as a mirror to reflect each side of the parabola. Now the parabola, unlike a line, does not have a constant rate of change. There are certain parts of the parabola on which it is increasing. Now since we always read on a graph from left to right, we look at the section to the right of the axis of symmetry as being where the graph is increasing, or where the function is increasing. We're going up as we go from left to right, and so the function is increasing when x is greater than 1. Similarly, as we go from left to right, the function decreases. It goes down on the left side of the axis of symmetry. We go from left to right, the y value decreases, and therefore we say that the function is decreasing when x is less than 1. So, when we look at the two sections here where the graph is decreasing or increasing, we're comparing the y's, the behavior of the y's, as the x moves from left to right. We don't say that the graph is either increasing or decreasing at the vertex. It's actually doing neither at that time. That's more of an advanced topic that you'll cover in future math classes, but something I can mention now. Now the domain is whatever the x values are. You can see from this graph, and it's not perfect, but it looks like it's going to continue on upward and outward pretty much forever. And for most parabolas, and all the parabolas that we're going to look at, which are y equals ax squared, our domain can be any value of x. So we call that all real numbers. And we could use this symbol for r, kind of an r with a double spine, and that's a symbol for all real numbers. Now the range is all of the y values, and we are going to continue up this way, but we're definitely not going to get any lower than our vertex because we've come down, we've decreased, and now we're going to increase. So we're never again going to get any lower. Therefore, our range, which is our set of acceptable y values, is going to be that y is greater than or equal to -5. It can be any y value higher than -5, and I obviously, based on this point here, the vertex, I can actually be at -5. So those are the characteristics of the parabola. Hope this was clear. Okay, I've put another parabola up here. I want you to try to figure out all the different characteristics of it. So pause the video, try to write down these characteristics, and then check back to see your answers. All right, let's see what we have. So there you go. The vertex is at -4, 3. The axis of symmetry is the vertical line x equals -4. The function increases when x is less than -4 and decreases when x is greater than -4. The domain is all real numbers, and the range is y is less than or equal to 3. If this wasn't clear, it's not exactly what you had, go back and watch the last slide and then try again. When we want to go and graph a certain equation, y equals ax squared, one method that I can use is a table or a t-chart. And so what I'm going to do is just pick out different values for x and plug them into my equation and figure out where those points go, graph them, connect them, and see if we can form our parabola. For the first one, I want to do g of x equals 2x squared. So I have to figure out what values to choose for our x. Well, 0 is always a good choice. I'm actually going to put that right in the middle here because that's actually where I think my vertex is going to be. Now I'm going to go 2 points in either direction. So I'll put 1 and 2 because those are going to be pretty easy on the right. And I'm going to pick -1 and -2 on the left. Now I just plug in each of those into my function. Now when I plug in 0, I'm going to have 0 going in here for x. So 0 squared is 0 times 2 is 0. So I have the point 0, 0. When I plug in 1, 1 squared is 1 times 2 is 2. And when I plug in 2, 2 squared is 4 times 2 is 8. Now when I plug in -1, I'm squaring the -1, so I have to make sure that I square -1, which makes it into a positive, and then I multiply by 2, so I'm actually going to end up with 2 there. And same type of thing for -2, when I square that it becomes a +4, and doubling that gives me a +8. Now I should expect to have some symmetry here, and I do, because I have my axis of symmetry that's going to go through my vertex. So that's a good sign. I'm going to plot all of these points now. So I'm going to start with the point 0, 0, and then do 1, 2, and then do 2, 8, and then I'm going to do the negatives, -1, 2, and -2, 8, and now I'm just going to do my best to connect them in a smooth curve. And so it's not perfect. I'll show you what you just try to get them to connect and turn, not too harsh. It's a little tough on this here, but you get the general idea. And you can draw the arrows to show that it's going to continue up in that direction. Let's do the same thing for h of x. My suggestion for this, however, I'd still use 0, but if I plug in a certain number, I'm going to end up getting a number that has to be divided by 3, because I'm going to multiply by 1/3. So it's actually going to be pretty beneficial if I can pick multiples of 3 here. So I'm going to choose 3 and -3. And 6 and -6. I think I actually might run out of a little bit of space, but we can probably get a pretty good estimate. When I plug in 0, square that, multiply by 1/3, 0. Now I'm going to plug in 3, and I get 3 squared is 9, 1/3 of that is 3, and because I know how the symmetry works, when I plug in -3, that's going to be the case as well. And when I plug in 6, 6 squared is 36. Ooh, that's pretty big, because then 1/3 of that is 12. So 6, 12, boy, it's going to be somewhere kind of way up here, and this one's going to be somewhere way up here. So I'm actually not going to graph that completely, but I would have 12 on either side. So maybe just those 3 points will be enough. Going to graph 0, 0, which is the x and the y. Then I'm going to graph 3, 3. So there's 3, 3. And I'm going to graph negative 3, negative 3. I'll graph that. And then I'm just going to take those. I'm going to graph those together. And I have a different parabola. So you see that for all of these parabolas here, they actually have the same domain and range. The one that I had drawn originally is just the basic y equals x squared. But yeah, these all have the same domain and range, and they have the same vertex and axis of symmetry. They increase and decrease in the same regions. It just so happens that one is wider than x squared and one is more narrow. And that's the only difference. But to graph these, you're best off just plugging into the t-chart and pick convenient values. You know, if your coefficient's a fraction, like 1/3, use x values that are multiples of that number so that it gets cleared up a little bit. I hope this makes sense. Alright, here's another opportunity to plug in and find some values for x in order to graph our parabolas. Once again, I'm just going to start with 0 in the center of each of our tables here, because plugging in for 0 into these functions will give me 0 for a y value each time. Now I want to think about what I want to plug in. I notice that I'm using negative 1.5 x squared and negative 1/2. Those are both fractions with denominators of 2, and so I'm probably going to want to choose even numbers to plug in. So I'm going to go 2 and 4 on the right, and negative 2, negative 4 on the left. And hopefully I can actually use these for both, because my denominator in each one would be 2. Negative 1.5 could be written as negative 3 over 2. So now I'm just going to plug in. So if you use a calculator, you can plug in. Just make sure that anytime you square a negative, it becomes a positive, and then you multiply by the negative coefficient. So go ahead and fill those in, and then I will reveal the answers. Alright, let's see them. Alright, so there you go. Those are the function values when you plug in. Those are the y values for each of the x values that we've chosen. You can see that I'm probably not going to be able to graph 4, negative 24, or negative 4, negative 24, but that's okay. I'll have the 3 points from the middle that I can graph. So I'll graph that function first. 0, 0 is certainly still in play. Negative 2, negative 6, and same thing for 2, 6. And I said, again, I can't graph all the way, it's way down here. So I'll just connect what I can. And it's it's a parabola. It's going to be kind of narrow compared to the y equals negative x squared that's shown. And now I will graph the other one. We've still got 0, 0 in the mix. We've got 2, negative 2, and negative 2, negative 2. And then we have 4, negative 8, and negative 4, negative 8. And then I just going to gradually connect these 5 points. And it's not going to be perfect. You can't be perfect. You can just get a pretty decent sketch. And that's what we have there. So just like on the last example, they have the same vertex, axis of symmetry, domain, range, and intervals where it's increasing and decreasing. The only thing that changes is if it's wider or narrower. So once again, if you're given a function, just pick values for x, plug them in to the function to find values for y, and then you can plot those points and connect them in a smooth way. You don't want to make it all herky-jerky or really pointed. Nice smooth curve to form your parabola. So you've seen from all of our examples so far that these graphs of parabolas, y equals ax squared, have a lot in common. The only thing that changes is how it opens in terms of opening up, down, narrow, or wide. And here we have a whole bunch of examples compiled to see how the number a, what it is, how that affects the type of curve that we have. If a is positive, the parabola is going to open up, like these three examples here. Here we have a is a positive 0.25, positive 1, positive 4. All these parabolas open up. If a is negative, like these parabolas down here, where our a is negative 0.25, negative 1, and negative 4, the parabola will open down. That's going to be true going forward. And also it's the size of the a that matters. If a is a big number, as in bigger than 1, like 4, or negative 4, since we can think about its absolute value, it's going to become a narrower function than the typical x squared or the typical negative x squared. It gets narrowed because it's being stretched out vertically. It's getting stretched out, and that makes it taller and narrower. Meanwhile, if it's a fraction between 0 and 1, if we think about its absolute value, then we're going to have something like 1/4, which is what 0.25 is, or negative 1/4, is going to make it a wider parabola. It's going to be kind of squished down and pulled out, made wider. So that's what you can expect. It's something that can be useful when we're comparing our answers, looking at something and knowing how it should look compared to a standard y equals x squared parabola. Let's just take a look at a pretty basic word problem here. There's a bridge that has an arch support that can be modeled by the function f of x equals negative 0.0012x squared. And this is the arch support here, where x and f of x are measured in feet. We want to find the height and width of the arch. This is really nothing more than just looking at the graph of this function. First of all, it has the behavior that we expect. Vertex at 0, 0, axis of symmetry, x equals 0. The fact that a here is a negative number, but a small number, absolute value less than 1, tells us this is going to, first of all, open down, being negative, which it does, and be very wide, which this certainly appears to be, because it's such a small number in terms of its absolute value. So it just matches our description that we had before. It increases when x is less than 0 and decreases when x is greater than 0. Kind of covers all of our characteristics. But in terms of its height and width, it's really nothing more than just looking at the graph. The height can be measured by figuring out exactly how far down this goes. And it goes down all the way to this point here. Based on that grid, each block appears to represent 50, so we're talking about a distance here of 300, which means that the height we're looking for, we have to make sure we put a proper label on it, is going to be 300 feet. That's quite a tall bridge support, but it pales in comparison to its width, because based on this here, we can see that the width, the bridge seems to go all the way out to 500. Now, because of the axis of symmetry, that's going to tell me that I've got 500 on the other side too. And based on that, I can identify pretty easily the width of this, and I know therefore that the width is 500 plus 500, or 1,000 feet. And so that's just a little question you can answer, and you can kind of examine it based on the nature of the parabola and its function expression. And there you go. I hope all of this makes a lot of sense.